Welcome everyone. In this video lecture, we will think about why power amplifier, okay, and concept of total harmonic distortion. So before that, we will go for the power amplifier. We have to know a basic concept of multi-stage amplifier. So basically, a multi-stage amplifier is used to deliver a large amount of power to load. Okay, so multi-stage amplifier means it consists of a number of amplifier stages. Okay, so for this purpose I am drawing some series of amplifier. Okay, so for example, say this one is one amplifier. Okay, this one is the third one. Okay, third is okay, and one more I will add. Okay, so in multi-stage amplifier, so multi-stage amplifier consists of a number of amplifiers. Okay, so I am saying the first one is say yours amplifier 1, amplifier say 1. Okay, similarly the second one is our amplifier 2, amplifier 3, and amplifier, oh sorry, or you just don't write anything for this one. Why? This one will be the our power amplifier I will discuss. So basically there are series of amplifier. In multi-stage amplifier is used to deliver a large amount of power to some load. Okay, so basically, and all are connected in cascade manner. Okay, all are connected in the cascade manner. Okay, clear. And I am saying this one having this amplifier having a gain 100. Okay, each amplifier having a gain 100. Okay, we are assuming each amplifier having a gain 100. Okay, clear. Then after I am saying we are giving a voltage, input voltage Vi. Okay, input voltage around 1 microvolt. Okay, so when we are giving a voltage 1 microvolt, so the output of this, say I am saying this one is our V naught 1. So A is the gain. Okay, so A is basically the V naught 1 by Vi. Okay, so one can write the V naught 1 is nothing but simply A times of Vi. So here we see A is 100 into 1 microampere. So can we write this is simply our what, 100 microvolt. Is it okay? Means V naught 1 is simply 100 microvolt. Similarly, if we go for this one, the output of V naught 2, because this one is connected, so V naught 2 is simply just 100 into 100. Okay, microvolt. So can we write directly 10 to the power 4 microvolt. Okay, or you can use this kind of formula. V naught 2 equals to what? Simply, okay, I am writing here. V naught 2 is A times of V naught 1. So A is again 100 into this one will be V naught 1 is 100 microvolt. Okay, so we can write as 10 to power 4 microvolt. And here what we have written 100 into 1 microvolt. So it is 100 microvolt that we have written here. Okay, similarly if we pass to the third amplifier, say I am saying this one is your output V naught 3. So the output will be 10 to power 6 microvolt, means nothing but simply 1 volt. Okay, 1 volt. So once again the V naught 3. Okay, the V naught 3 is simply A times of V naught 2. Okay, so A is 100 and 10 to power 4 microvolt means 10 to power 6 into 10 to power minus 6, because micro is this one. So it is simply our 1 volt. So see here the signal strength is very low. Okay, very low. The signal strength is very low here. Okay, then after the signal strength become what, 100 microvolt. Is it okay? 100 microvolt. The signal strength become 100 microvolt. Then 10 to the power 4. Okay, 10 to the power 4. Then finally see microvolt. Now here what we observe, we get around 1 volt. Okay, so the signal strength at this stage is very high. So now if we have to drive such high voltage to the load, okay, if we have to drive such high voltage to the load, say some load is there, if we have to drive this very high voltage to a load without the loss of the signal, we need an amplifier that is called our power amplifier. Okay, so this amplifier is we can call as power amplifier. I will tell you some name, basic name of the power amplifier. So this one is our power amplifier, and the last stage, this last stage we are saying this one is the last stage. Okay, we can say this last stage is also called as is also called as output stage. Output stage, okay, of an amplifier. Okay, so the last stage of this amplifier is called the output stage. Okay, which is nothing but simply made of a special kind of transistor. It may be MOSFET or BJT to drive the large signal. Okay, so the this one, the last amplifier stage is nothing but simply the multi-stage amplifier, which is called the output stage of the power amplifier, which is a special type of transistor to drive the large signal. So I'm just writing the same thing here that I have taught. Means the last stage of amplifier stage is a multi-stage in a multi-stage amplifier is called the output stage. Okay, it's called the output stage. Okay, this output stage, which is a special type of transistor, type of power transistor, we are saying power transistor, to drive the large signal. Okay, so what is the special kind of transistor? Okay, so that transistor, suppose we are saying BJT based. Okay, example I am saying, for example. Okay, example, I think you have heard about the power transistor. Suppose one transistor, I am writing TIP 3055. It is a power transistor, okay, that can drive, and it is a NPN transistor, NPN BJT, NPN BJT, okay. And another one we can say TIP 2955, okay, it is our PNP transistor. Okay, these are the BJT. Okay, these are the BJT transistor. BJT transistor or BJT we can also say. So this one is the commonly used transistor. Okay, for the means to drive the very high signal. Okay, NPN TIP 3055, TIP 2955. So one more example for the MOSFET that I will give you. For example, uh, N channel MOSFET. Okay, but power one. So it is simply our. So the name is, I think, IRF. IRF 5. IRF 540. Okay, wait. This one is IRF 540. Okay, this one is our N channel MOSFET. N channel power MOSFET. We can say N channel power MOSFET. Okay, and another one is our IRF. Okay, 9540 P channel power MOSFET. or MOSFET, N channel. Okay, sorry, P channel. So these are the some, means what we can say, the uh, basic amplifier, power amplifier, which are used, okay, to drive a very high signal. Okay, see here what signal we are getting, 1 volt. Okay, we have started 1 micro, very this. Okay, the this one is very small, 10 to the power minus 6 to 10 to the power minus 6 to 1 volt we are, it came. So we required a very powerful transistor, that is our power amplifier. So these are the some example. So we can say, okay, I am highlighting this part also, because this one is some important name that you have to know for NPN PNP, and another one is our what? Okay, clear. So one thing is clear, means we have started with what, 10 to power minus 6. Okay, we have started with here 10 to power minus 6. See, this one is 10 to power minus 6 volt. Okay, this volt is 10 to power minus 6, and now what we are getting, 1 volt. Okay, so we required a special kind of transistor. It's called our power amplifier. Now, next. So that's the region. Okay. Hence, the power transistor. Okay. So one more thing, that so output stage of the amplifier must have low output resistance. So the thing is that the output stage of the amplifier must have low output resistance. Okay. The output resistance must be low, and it can deliver the output high signal 1 volt to the load without loss of gain. Is it okay? Clear? Means output stage amplifier must have very low output resistance, and it can deliver the output signal of 1 volt. Here we have taken the 1 volt, so it may be more also, but here we have started with 10 to the minus 6 and 4 stages. So 1 volt to the load without loss of gain. So that's the region we have used this one. Okay, so hence the power transistor, we can say, hence the power transistor as a power amplifier can be used to, at the output stage, to drive a very high signal without any loss, ideally. Okay, so this is the, we can say, the region. Okay, so I'm just copying this. Is it clear? Okay, so actually I have already written initially, so make it point. Okay, and signal. Okay, I will write signal. Clear? So hence the power amplifier, or we can say the power transistor, at the output stage, final stage, is used to drive high signal strength without any loss, ideally, ideal case. This one is the ideal one. Okay, so this is the reason why we have used the power amplifier. Is it okay? So now our next topic is our what, total harmonic distortion. Okay, so we will start total harmonic distortion. For this purpose, I have already written the definition. Okay, so wait for a minute. Okay, so now our topic is total harmonic distortion. Okay, so basically, total harmonic distortion (THD) is used to measure the goodness of the amplifier. The amplifier is good or suitable for not. We can, how we will measure, some measuring tool or method. So basically, THD is a method to measure the goodness of the amplifier design at the output stage. Okay, THD is a method to measure the goodness of the amplifier design. I will show you the formula also, but this one is the some definition. Okay, means why we have used THD to measure the goodness of the amplifier design. Okay, how much suitability or how much effective an amplifier is, how we will justify through THD. Okay, so basically it is the RMS value of the harmonic component of the output stage or output signal, excluding the fundamental one that I will cover, and expressed as a percentage of the RMS of the fundamental. Okay, so for this purpose I will go with an example. Okay, this how to find. Okay, so basically for this purpose, suppose, okay, I am taking a, okay, a BJT. Okay, so suppose I am just using a BJT. Okay, I am writing here BJT. Okay, BJT. So what I am saying is there is a BJT. Okay, and we are giving some signal. Okay, and we are getting some output. So suppose we are giving both AC, that is our VBE, and some DC component VBE. Okay, in my small signal analysis lecture I have already covered this kind of concept. Means if this one is our transistor, okay, so, and we are giving some AC signal along with DC. Okay, so make it say this one is our VBE. So this one is a AC and DC. So the instantaneous one is represented as a small v, and the subscript will be in the capital letter. In both the symbol as well as the subscript, okay, VBE is the subscript, okay. Here it is not looks like subscript, okay. VBE is our AC symbol as well as the subscript in the small letter. V, capital V, BE is the DC one, okay, and this one is the instantaneous one, instantaneous voltage, instantaneous voltage, okay, that is our V small and this one is capital. So basically this VBE is what? AC plus DC. The instantaneous must component have VBE plus VB. I have already covered this one in my earlier video for the small signal analysis and all. And I am saying this current is our instantaneous current. Okay, so that instantaneous current what we are getting, I'm just writing like this: IC is some DC component plus AC component. Okay, AC component. Okay, and this AC current is basically a periodic, but we it is periodic but not proper sinusoidal signal, but not proper sinusoidal signal. Okay, for that purpose we have to use Fourier series. Okay, so Fourier series allows us to express a given periodic signal in terms of infinite number of sinusoid. Okay, so now the instantaneous collector current, what we can write, IC is basically IC DC component plus AC component. So this AC component must have some IC. Okay, so basically if we solve, we will get GM times of VBE, and then VBE is a signal. VBE is a signal. Okay, VBE is a signal. Clear? VBE is a signal. But if we get the output across, so it is not proper sinusoidal. So we have to, but it is periodic. So we have to express in terms of infinite number of sinusoids. Okay, so we can write the expression this one, some DC component like IC dash we can write plus IC1. Okay, some sinusoidal component will come. So we can write like this: IC1, IC2 cos 2 omega t plus IC3 3 omega t plus dot 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 dot. Through Fourier series. To allow through Fourier series, we have expressed a given periodic signal in terms of infinite number of sinusoids. Okay. Through Fourier series, we have applied the Fourier series and we have written like this. So one more line we can write this as a IC double dash, some DC component. These two is the, say I am saying these two are the DC components. So we are saying this one is nothing but simply IC double dash. Okay. And another one that we have already written. Okay, so one more line I will write IC1 cos omega t plus IC2 cos 2 omega t plus dot 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 dot. So this one, the first one is our DC component we can write, and the another one DC component, and this one is our fundamental component, fundamental component, and these are the, we can say, the distortion component. Okay, clear. So now these are, we can say that it is in the harmonics. Okay, it is in the harmonics. First and second harmonics, third harmonics, fourth harmonics, like that. Okay, so second harmonics. So we can write. Okay, I'm writing here the second harmonics. Okay, second harmonics, and I am saying that is our D2. So this one is our second harmonics D2, can be written as IC2, this one, second harmonics IC2 by the fundamental one, IC1. Okay. Similarly, for the third harmonics, okay, will be, I am saying D3. D3 is simply IC3 by fundamental one. Okay. Similarly, the fourth harmonic, okay, fourth harmonics component, you can also write harmonics, okay, or fourth harmonic distortion, better to write distortion. Okay, that is our D4 will be IC4 by IC1, like that. Okay, clear this one. Now the fundamental AC power, now one term I am saying fundamental fundamental AC power, we can write as IC1 square by 2 into some resistance R. Okay, for example, say some resistance is there, R naught. Okay, so some resistance is R naught. So power in R naught resistance, okay, will be just I RMS square into R. Okay, and this will be Im by root 2 square into R naught. So we can write a Im square by 2 R naught. So that's why I am writing this as a power is simply, okay, clear this thing, clear, fundamental AC power. Okay, now total harmonic power, what should be the total harmonic power? Total harmonic power, so for this purpose what we can write here, I am writing total harmonic total harmonic power. So total harmonic power, how we will write, say I am writing total harmonic power as PT. Okay, so PT is nothing but simply the sum of IC1 square by IC1 square by 2, okay, into R naught plus IC2 square by 2 into R naught plus IC3, sorry, IC3 square, right, is 2 into R naught plus dot dot. Okay, so now what we can take, if we take the common IC1 square by R naught, sorry, are not in the by 2, it should be written as 1 plus IC2 by IC1, okay, square plus one more component I can write IC3 by IC1 whole square plus dot 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 dot, okay. So now what we observe that this one is nothing but simply the first one. The first one we can say the power P1, okay. So this one we can say this one is our power P1, okay, this component. And the another one is our IC2 by IC1 is nothing but simply distortion component, second harmonic distortion 22 square plus D3 square plus dot 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 dot, okay. So this PT can be written as 1, sorry, 1 plus polar d square into p, okay, because this pt equals to p1 plus d square, okay, because this whole term will be our d. So this is the expression for power dissipation 1 plus d square, because thd, this one is our thd. So one line also I will write thd, okay. thd is what? D equals to d d square plus d3 square plus d4 square. Actually my battery is going to die. Okay, so this is all about this lecture. So thank you for watching this video. Thank you.